Hello everyone, welcome to section 8.2. In this section, what we're going to learn to do is how can we hand draw polar equations? Or what we want to do is we want to start graphing polar equations. So let's get started. The first thing we need to do is we need to use what's called a polar grid or the polar axis. So let's go ahead and draw one really quick. Okay, so we can first start by drawing our kind of XY axes. And remember how polar coordinates work. We are going to have some sort of angle, a certain amount that we're going to rotate. And once we rotate that amount, we want to know from that angle how far should we go out, I guess if the radius is positive, or how far should I go backwards if the radius is negative. So one thing we want to do here is we actually want to plot, these lines or these circles of constant radiuses. So before we do that, let's take a look at the example that we're going to graph first. We're first going to graph r is equal to 2 cosine of theta. Well, if you think about this, what is the largest possible radius that we can get? Well, no matter, I guess, regardless of what the angle is, or I guess another way to think, or what I'm trying to say is, what is the range of cosine of theta? Cosine of theta is only going to spit out numbers between -1 and 1. So the biggest thing that cosine can spit out is 1, and 1 times 2 will be 2. So the biggest possible radius that we can get will be 2. So we at least want to have a circle of radius 2. Let's also have a circle of radius 1. So we're going to have 2 steps here. So here's 1. So roughly go out 1 unit. This doesn't have to be exact. Just want to get a rough idea of how to graph polar equations. Okay, so circle of radius 1. Let's also do a circle of radius 2. So 2 units. 2 units. 2 units. All right, so let's attempt, sorry I'm blocking the camera, but let's try to draw perfect circles. Hand drawn, so they won't be perfect, just something that's almost a perfect circle. So there's a circle of radius 1. How about a circle of radius 2? Okay. So anywhere on the circle, the radius will always be 1. Anywhere on this circle, the radius will always be 2. Now we also want to mark angles. So I'm going to start by doing a 45-degree angle or a pi over 4 radian angle. So that one's pretty easy to eyeball. Okay, we can do one that has a negative pi over 4 angle. Okay. And now let's mark pi over 6 and pi over 3. So what I like to do is I just go halfway along one of the axes. So let's say if I go halfway along the y-axis and I go over, well, this angle right here will be pi over 3. I'm sorry, pi over 6. So here's an angle of pi over 6, and we're just going to go backwards. Okay, similarly, if we go halfway along the x between 0 and 1, if we go halfway and go up, this will be an angle of pi over 3. And again, this doesn't have to be perfect. Just enough till we have some guiding, some guidance. Okay, so here we have our polar grid. So this would be an angle of pi over 6, pi over 4, pi over 3, pi over 2, so on and so forth. Okay. So let's go ahead and now plot this equation. Now before we, I guess whenever you're first doing something in math and you're not really sure, you don't really kind of have your feet grounded, the best thing to do is just make a t-table. We're just going to do a table of inputs and outputs. So what I have here is I'm going to plug in an angle of 0, so 0 radians into this function, and out's going to pop out the radius. So if we plug in 0 for theta, we get 2 times the cosine of 0. Well, cosine of 0 is 1, so we'll get an output of 2. Okay, so where is that going to be? Where is that going to be? So this is saying that if we rotate 0 degrees, our radius will be 2. So we rotate 0 degrees, which means we really haven't rotated. We're not off the x-axis yet. We'd be at a radius of 2. So this point here will be on our graph. Okay, similarly, if you plug in pi over 6, if we plug in pi over 6, I have r is equal to 2 times cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. Root 3 over 2 times 2, that just gives us root 3. But we'll just use our calculators and we'll hopefully get 1.7. So if we rotate an angle of pi over 6, that means we need to go out a radius of roughly 1.7. So rotating pi over 6, if I go out to this first circle, that's 1 unit out. This would be 2 units out. We need to go roughly 1.7. So I don't know, maybe roughly 1.7 is roughly right here. So this is pi over 6 and a radius of 1.7. Okay, we're just going to go through and we're just going to keep plotting these points here. I do kind of want to make a note here that notice I kind of stopped at 7 pi over 6. Well, I was noticing there was some repetition that was happening. I got 1.7, 1.4, 1, 0, then I got negative 1, then negative 1.4, then negative 1.7, then a negative 2. And now I'm getting negative 1.7, so we're kind of just going backwards. It's going to start repeating itself. Okay, so let's continue plotting points. So if we rotate an angle of pi over 4, we'll be at a radius of 1.4. So rotate pi over 4, well, radius of 1.4, well, this is roughly 1, that's like 1.5, I don't know, 1.4 is maybe roughly right here. Okay, we'll continue on. If we rotate an angle of pi over 3, we'll need to go out a radius of 1. So here we have now rotated an angle of pi over 3, and now we need to go out 1 unit. So we'll mark this spot right here. Okay, now when we rotate an angle of pi over 2, so that's what, 90 degrees, we are going to be at a radius of 0. So now we're back at the origin. Whenever the radius is 0, that means we're at the origin. We're at 0, 0 in rectangular coordinates. Well, I guess that would be the same thing in polar coordinates, 0, 0. But we'll be at the origin. So we'll be right back here. Now, let's just kind of notice something, what's happening as we're rotating from 0 degrees or 0 radians to pi over 2 radians. As we're going from 0 radians to pi over 2 radians, what is the radius doing? What is the radius doing? It's starting out at 2 and it's decreasing. It's decreasing till we get to 0. So at an angle of 0, we're out 2 units. And as we rotate, the radius is decreasing, which means my arm is getting closer to the origin as we rotate. So as we rotate, the radius is decreasing. As we rotate, the radius is decreasing. So now when we're at an angle of pi over 2, we're at a radius of 0. Okay, let's keep going. Okay, now if we're at an angle of 2 pi over 3, we need to go out a radius of negative 1. So here's 2 pi over 3. Now we need to go to a radius of negative 1. If the radius was positive 1, we would go here. But it's a radius of negative 1, so we go in the other direction, so we need to go out here 1 unit. So an angle of 2 pi over 3, but the radius is negative 1. Okay. Now, if we rotate 3 pi over 4, we'll have a radius of negative 1.4. So here we've rotated 3 pi over 4. Now we need to go out, or in the other direction, because it's negative, roughly 1.4 units. So 1, 1.5, I don't know, 1.4. This will be an angle of 3 pi over 4 and a radius of negative 1.4. Okay, at 5 pi over 6, we need to rotate negative 1.7. I hope you're seeing there's a bunch of symmetry going on now. So if we now rotate, 5 pi over 6, so 5 pi over 6, the radius is going to be negative 1.7. So we'll go backwards 1, 2, go back a little bit. This is roughly, a radius of negative 1.7 if we rotate 5 pi over 6. Okay, now if we rotate pi? If we rotate pi, now we'll be at negative 2. So we'll rotate pi, but now I need to go a radius of negative 2, so we're back right where we started. We're back right where we started. So notice here, as we rotate from pi over 2 to pi, from pi over 2 to pi, what's happening is, sure, the radius is negative, but the radius is getting more negative. So as we rotate, the radius is, it's negative, so on the other side of the angle, but it's getting more negative as we rotate around. It's getting more negative as we rotate around. Boom. Awesome. Okay, now notice if we were at 7 pi over 6, so 7 pi over 6, that would be this angle here. Sorry. 7 pi over 6. We'd be at an angle of negative 1.7, so 5 pi over 6, negative 1.7 would now be right back here. So we're just going to start repeating ourselves. So this is the graph. And in this case, we can recognize what this graph is, or we have a good name for it. This is a circle of what? This is a circle. This is a circle of, what's the radius? 1. Circle of radius 1. Let's say what? Width. With center, where's the center? At what? 1? At the coordinates 1, 0. Now what's great here is we could have actually recognized this without having to plot in polar coordinates if we would have transformed it into rectangular coordinates. Let's just do that really quick. So if we want to put this into rectangular coordinates, I want r squared pieces to show up. I want r cosines to show up so I can replace it with x. I want r sines to show up so we can replace that with y. Okay, so I think multiplying both sides of this equation by r will be helpful. So then what are we going to get? We're going to get r squared is going to be equal to 2 times r cosine of theta. Well, this r squared can be replaced with x squared plus y squared. That's going to be equal to what? 2. This gets replaced with what? X. So we have now transformed this into rectangular coordinates, but hopefully this is a pattern that we can recognize that we could complete the square on this. So here, let's write x squared. Let's subtract 2x. Plus a y squared will be equal to 0. So I just subtracted 2x from both sides. Well, I have an x squared minus 2x. This thing is begging to be completed the square on. So what do I need to add here? Well, we take the middle coefficient, or the coefficient in front of x, negative 2. You cut that in half and you square it. So what? That's going to be a negative 1 squared, or we need to add a 1. So if we add 1 here, we also have to also add 1 to the other side. So this now factors to what? An x minus 1 quantity squared plus a y squared will be equal to 1, which I hope we recognize is a circle of radius 1, but it's been shifted to the right 1 unit. Beautiful. Okay, let's go ahead and do a different example. What I would say was very tedious about this example here is that, well, we had to make a t-table, and even though I kind of had it on the board for us, when the video started, I mean, it's a pain in the butt, using your calculator, inputs, outputs. It'd be nice if we could do this much quicker, and that's what I'm going to show you in the next example. Let's take a look at this next example. What we're going to do here is instead of making a t-table, we're going to make a graphical t-table. And the way we're going to do that is we're going to think about theta kind of being like x if it's in rectangular coordinates. And we're going to think of our radius as kind of like our y in rectangular coordinates. And we're going to plot this as if it was in rectangular coordinates. Okay, so we have a radius of 3, or sorry, an amplitude of 3. So here's 3. Negative 3. The period is 2 pi. Okay, sine starts at equilibrium. So here's the graph of 3 sine of theta, at least a rough graph. Okay. But what I want to look here is this is really a graphical t-table. What I have on the y-axis is the radius, and what I have on the x-axis is the angle. So what we can do is we can just kind of read what the radius and angle are from here. So notice that this is saying that if we rotate a radius, if we rotate an angle of 0 radians, my radius would be 0. So if we rotate 0 radians, we're at an angle, our radius is 0. So we're starting here at the origin. Now what happens as we move? Well, let's say we go over to pi over 2, for example. This is saying that if we rotate an angle of pi over 2, the radius will be 3. So it's almost like we're taking these radiuses. The height here represents the radius. So here, this would be a radius of 3. So at an angle of pi over 2, the radius is 3. An angle of pi over 2, the radius is 3. Okay? So, if we kind of go back a little bit, if we're kind of eyeballing this, if we are at, this will be roughly pi over 4. If we're at pi over 4, looks like the radius I don't know, looks like to be something between 2 and 3. So if we rotate pi over 4, the radius is, a little bit bigger than 2. Rotating pi over 4, the radius is bigger than 2. We'll mark a spot right here. But the key thing to do when you're looking at this is noticing what the radiuses are doing when we move across. So notice that as we start at 0 degrees, when we rotate, notice that the radiuses are getting larger. They're getting larger at first, and then they're going down. So the radiuses, if we're rotating from 0 radians to pi radians, or how about 0 radians to pi over 2 radians, the radiuses are increasing. So as we rotate, I should be going further away. I should be going further away from the origin. As we rotate, we should be going further away. So we have this right here. Okay? Now we're at pi over 2. What happens between pi over 2 and pi? Well, as we rotate between pi over 2 and pi, the radiuses are decreasing. So we're right here. As we go towards pi radians, my radius should be getting closer to the origin. We should be getting closer to the origin. My radius starts out at 3 at pi over 2 and is going towards 0. Let's try and draw that. Here we go. So I guess if you want to be a little bit more precise, I don't know, this is going to be symmetric. It's going to be symmetric. I'll be doing something like this. Oh, by symmetric, I mean right here. Okay, there we go. I'm noticing symmetry here because from here to here it goes up, and then from here to here it goes down, so I knew it had to be symmetric here. Okay, so what do we have here? We now have this circle. We have a circle, again, what is this? A circle of radius, this would be a circle of radius 1.5, and its center would be at what? An x coordinate of 0 and a y coordinate of 1.5. But what's great is it was a lot easier for us to look at this graph here than to make this giant t-table. Now, what I would like to kind of make note when we're doing this is wherever you see an x-intercept or a theta intercept, this is when the radiuses are 0. These correspond to the origin. These correspond to the origin. And a good thing to think about on this first kind of upper loop right here, this is saying that when we rotate between 0 and pi, so I'm going to mark that, so when we're rotating from 0 radians to pi radians, I know what's going to happen is my radius, I'm going to start at the origin, my radius gets bigger, and then I go back to the origin. So I almost know that I kind of have to have between 0 radians and pi radians, I have to have some sort of loop. Because as we're going around, the radius is getting bigger, but then it's going to return back to 0. So this kind of piece that is above the x-axis, this is telling you that there's a loop that's happening. The radius, as we rotate, the radius goes out and then it comes back in. This is going to be kind of like what I'll say, like a leaf. It's like a little, I don't know, I think that's the best way to say it. It's like kind of like a little leaf. Okay? And I know that leaf is going to be contained between 0 to 0 radians and pi over 2 radians. We'll do more examples here in just a second. Okay, but if we were to continue rotating, well, this could possibly be another leaf to our graph, but it turns out for this specific example, this part of the leaf goes back over, the leaves are on top of one another. You'll see with another example here in just a moment. But this is saying, we think about these radiuses. These are all negative radiuses. So when we're at pi radians, we have a radius of 0, but as we rotate, let's say from pi to 3 pi over 2, from pi to 3 pi over 2, well, my radius starts at 0, and then my radius goes to -3. So we're not going to go with the angle, we're going to go against it. So as we rotate around, the radius starts at 0, goes to -3, starts at 0, goes to -3. So what's happening here is this leaf for this bottom part is just running right back over the top of this one here. So it actually is going to start repeating itself. Let's do another example. Let me illustrate these leaves by changing the period of this graph. Let's try to see what happens if we now graph 3 sine of 2 theta. Pause the video and give this a shot. Okay, let's do it. Let's first make our graphical t-table. And for a lot of these problems, you're going to want to plot them out to 2 pi. Because we want to know what the radius is doing as we go around the circle at least one time. Okay, so for 3 sine of theta, okay, what's the period? Well, the period would be, what, you take 2 pi and you divide it by the number out front, so 2. So the period is pi. Okay, so let's put pi here. Here's 2 pi. Okay, here is pi over 4, I'm sorry, pi over 2. And pi over 4, 1, 2, 3 pi over 4. 5, and then 3, 4, 5, 6, 7. So this will be 6, 5 pi over 2. This is over 4, 6 pi over 4, and 7 pi over 4. There we go. Okay, so 6 pi, 6 halves, so that's 6 fourths, that's 3 halves. There we go. Okay, the amplitude is 3, -3. Okay, sine starts at equilibrium. Okay, so it's going to bounce. Okay, so here will be 1 period. Okay, let's keep going. So in this case, we'll graph 2 periods. Okay, so here we have it. Okay, so let's start. Let's notice something here. I guess the thing is what I like to notice is, well, between 0 and pi over 2, what's going to happen? The radius is going to get bigger, and then it's going to go back down. So all of these locations are where the graph is at the origin. At origin. That's when the radius is 0. So when we sweep out an angle between 0 radians and pi over 2 radians, what is the radius doing? It's going to get bigger. The radius is going to get bigger. It's going to start at 0, it's going to get bigger, and then it's going to go back down to 0. Within 0 and pi over 2, the radius is going to go out and come back in. So we have like a leaf right here. We have a leaf right here in between these x-intercepts. Okay, and that leaf is going to be contained between an angle of 0 radians and pi over 2 radians. So within here, the radius is going to go out, it's going to be getting bigger, and then it's going to come back down to 0. And right at pi over 4, it's going to be a radius of 3. So what is this graph doing? it's going to be going out, it's going to be getting bigger, and then it's going to come back, and then it's going to come back. Okay, so this is just a loose, again, this is just a loose sketch. But I'm going to have a leaf here. I'm going to return to the origin. We're going to start at the origin. We're going to go away from the origin, and then we're going to return back to the origin, all between rotating between 0 and pi over 2. Okay, different color. Okay, now what's going to happen between here and here? Here we're going to have another leaf in our graph. Another leaf. And this leaf is going to be contained between going pi over 2 and pi. Okay, so I'm going to draw that. Okay, here's pi over 2, and here's 3, and here's pi. Okay, so depending if the radius is in positive or negative, we're going to be rotating between pi over 2, between pi over 2 and pi. So if the radius was positive, the entire leaf would be contained in here. However, since the radius is negative in here, as we rotate from pi over 2 to pi, the radius is going to be negative, so we're actually going to get an entire loop or a piece of the leaf in, I guess this would be the 4th quadrant. So this piece right here, the radius is 0, then the radius becomes more negative until we're at an angle of 3 pi over 4. Well, what? 3 pi over 4, the radius is negative 3. So what's going to be happening as we rotate between pi over 2 and pi, we're going to get a leaf, but because the radius is negative, this leaf is going to happen over here. How cool. Okay. Well, then what's going to happen, I only got, so many colors. Okay, now what's going to happen here? Green. Okay. Well, now between pi and 3 pi over 2, between pi and 3 pi over 2, pi and 3 pi over 2, well, I'm going to have a leaf in here. Now, the leaf is either going to be in this quadrant or this quadrant, depending if the radius is positive or negative, but between pi and 3 pi over 2, the radiuses are positive. So as we rotate from pi, we're at 0. Now, as we rotate, the radius is going to be getting bigger, and then it's going to go back down to 0. So the radius is going to be getting bigger as we rotate, and then it's going to come back to 0. So we'll get this leaf right here. How cool. All right, I need more colors. Oh, we got a purple. Okay. Now we have this last piece right here. Okay, well, where is this happening between? Well, this is happening between 3 pi over 2, between 3 pi over 2 and 2 pi. So I'm going to be rotating from here to here. Well, if my radius is positive, I will stay in the 4th quadrant. But if my radius is negative, I'm going to reflect back into the 2nd quadrant. Notice in here, the radiuses are negative. They're getting more negative, and then they're getting less negative. So as we rotate around, the radiuses are getting more negative. We're getting more negative. We're getting more negative. And then they're going to be becoming less negative. That was an awful loop. But they're getting more negative. So now we're at what? What is it? 7 pi over 4. The radius is negative 3. And then we're going to come back. So that's how I like to think. When you're in between x-intercepts, there's going to be a leaf that happens. Now, in the previous example, those leaves were kind of going over top of one another. But for this example, these leaves are not on top of one another, and we get all of these here. Now, if we actually were to continue going, we would now be back here, and we would be doing the blue leaf again. So this graph goes. Okay. Let's do it. So as we rotate, the radius is getting bigger, and then we're going back to 0. Now we're still rotating this way, except now the radius is negative, getting more negative, and then back down to 0. And then over here, we're rotating over here, but the radius is positive. The radius is positive, so it goes. And then here we're going to rotate, but the radius is negative. Kind of cool. Let's do one more. Let's change this to, how about we change this to not 2 theta, but 3 theta. Okay, let's try and graph r equals 3 sine of 3 theta. Go ahead and pause the video and give this a shot. Let's do it. Okay, so I at least want to plot points as if we're going around the circle at least one time. Okay, what's the period? Well, the period here will be 2 pi divided by 3. So what I'm going to do is I'm actually going to take the entire 2 pi, I'm going to cut that into 3 pieces. So from here to here will be 2 pi, or you could think, go out 1 2 pi over 3. 2 pi over 3, 2 pi's over 3 would be 2 times 2, so it would be 4 pi over 3. And then 1, 2, 3, 4, 5, 6 pi's over 3 would be the same thing as 2 pi. So I have a region of 2 pi and I cut this into 3 pieces. And I should get one period of the graph in each one of these 3 spots. Okay, so I need to mark 4 spots in each of these. So if I cut this in half, what we're going to be at? If I cut this in half, I'll be at pi over 3. Okay, cut that in half again. Here we are at pi over 6. So we'll just count. So 1, 2, this will be 3 pi's over 6. So 1, 2, 3, 4 pi's over 6, 5, 5, 5, 5, 6, 7, 8, 9, 10, 11. So this will be 1, 2, 3, 4, 5 pi over 6. This will be 6 pi over 6. Or pi, then it'll be 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, and 11 pi over 6. Okay, we could reduce these, at least a few of them. Let's make this 3 halves, 5 thirds. And there we go. Okay, so we should get a period of sign in each of these pieces. Okay, there we go. Okay, so it looks like we could have quite a few leaves in this problem. Okay, let's take a look. Okay, for the very first one, we should notice that when we go between 0 radians and pi over 3 radians, the radius goes from 0, it gets all the way to 3, and goes back to 0. So between 0 radians and pi over 3 radians, we're going to get a leaf. Okay, so I'm going to draw that. Here's pi over 3, and here's 0. So when we rotate between 0 and pi over 3, we should be getting a leaf. And right at pi over 6, we'll be at 3. So if at pi over 6, here we are at 3. So the radius is going to go out, and then it's going to come back in. So here we have this first leaf right here. And since the radius is positive, I knew it was going to stay within this window right here. If it was negative, if the radius was negative, it would be over here instead. Okay, now between pi over 3 and 2 pi over 3, okay, so between pi over 3 and 2 pi over 3, so here's 2 pi over 3. Okay, we should be getting another leaf. So when we're between here and here, we should be getting another leaf. Okay, well, the radius is negative, so the leaf isn't going to live here. The leaf is going to live down here. So as we rotate between pi over 3 and 2 pi over 3, we're going to get out to a negative 3. This is actually, what it was, 3 pi over 6. This is pi over 2. This is the same thing as pi over 2. So when we are at pi over 2, the radius is negative 3. So as we rotate, the leaf is going to do this. Cool. Okay, now between 2 pi over 3 and pi, okay, we'll do that in red. Okay, between 2 pi over 3 and pi, so between here and here, okay, we should be getting another leaf, and the radiuses are positive, so it's going to stay within this window. So it's going to come back up. It's going to come back up, and right at 5 pi over 6, we're going to get a radius of 3. So it's going to come up, and it's going to come back down. And here we are. Okay, probably make that a little bit more symmetric. Okay, there we go. Okay, now what's going to happen? Okay, now what's going to happen when we go from pi to 4 pi over 3? So when we're going here from pi, here's pi, and here's 4 pi over 3. So we're rotating between here and here. This is where we're rotating. Well, the radius is always negative here. So it's always negative. It's going to be getting more negative and going back to negative, specifically at 7 pi over 6. Let's see, at 7 pi over 6, we're going to have a radius of negative 3. That puts us right back here. So when we rotate within here, we're actually going to loop back over this. And actually now the graph is going to start repeating itself. So we do have these nice kind of 3 leaves here, but then what's happened is these leaves are going to start going over one another. So this here is the graph of r, which is equal to 3 sine of 3 theta. Pretty cool. Okay, so we've actually taken these and we've looked at sine of theta, sine of 2 theta, sine of 3 theta. We've looked at kind of how changing the period changes the graph. What if we shift the graph up and down? Let's take a look at those. So the very first polar equation we graphed in this lecture was r being equal to 2 times the cosine of theta. Now we plotted this one with a t-table, but let's take a look at it as a graph. So let's say this is 2 pi, here's pi over 2, here's 3 pi over 2. Let's see. So cosine starts at the top of the amplitude. Okay, so here's one period of cosine. Okay, if we want to do a quick polar sketch of it, so here's, let's say, out a radius of 1. I'm going to say here out a radius of 2. Okay, so what's happening in this graph right here is, I guess you could almost think about having a loop that starts from here to here, and the loop isn't going to quite finish off until we go from here to here. Or you could think of the graph kind of going backwards if you'd like. So here's negative pi over 2. Here's negative pi over 2. So we should have a leaf. We should have a leaf between negative pi over 2 and pi over 2 if you like. So at negative pi over 2, this is negative pi over 2. And now we're going to go to pi over 2, so all the way over here. Okay. Within here, we are going to get a leaf. And the radius is going to be increasing and then decreasing. So at negative pi over 2, we have an angle of 0. Okay, and as we rotate, the radius gets bigger. It's going to be at 2 when we're at an angle of 0. And then it's going to go back to 0. So the graph, the radius is going to be increasing. The radius is going to be increasing and then decreasing. And this was that circle that we saw earlier. So I guess kind of just try to sketch it really quick. But what would be interesting is, what if we shift the graph slightly? Let's try to graph r equals 2 cosine of theta plus 1. Go ahead and pause the video and give it a shot on your own. Okay, let's do it together. Let's first graph r equals 2 cosine of theta plus 1. Okay, we're going to be thinking about theta on the x-axis and r on the y-axis. Okay, well, the period will be 2 pi. Okay, it's shifted up 1 unit. So we have an equilibrium at 1. It has an amplitude of 2, so we'll go up 2 from equilibrium. So here we are at 3. We need to go down 2 from equilibrium. So here we are at negative 1. Okay, let's kind of make our window. Okay, 2 pi. Here is pi. Here's pi over 2. 1, 2, 3 pi over 2. Okay, cosine starts at the top of the amplitude. And we'll go ahead and bounce. Okay. So the cosine, one period of cosine looks roughly something like this. For fun, let's go ahead and, I don't know, let's go back. Let's go back pi over 2. And I guess we could go over here. Negative pi. Trying to be a little bit symmetric. Here, I'll move in just a second. but kind of went back a little bit because I'm noticing that between those two x-intercepts here, I should have a loop, or what we'll notice is this will be the first part of the loop, or when the other part of the loop here could finish over here, however you want to think about it. But what I'm going to look at is I'm going to notice that we should be getting some sort of leaf or some sort of a loop for this kind of hump, and we should be getting another little leaf on this kind of smaller hump. Okay, let's see what happens. Let's first think about this leaf right here. So where is it going to be between? Well, what is this? This is somewhere between pi over 2 and pi. So pi over 2 and pi, something that's a little bit probably closer to pi over 2. So I don't know, I'm just going to kind of, I don't know exactly if it's at 2 pi over 3, but I don't know, it's somewhere around here. And between 3 pi over 2. Okay, let's see, between here and let's go backwards. How about negative? We'll go negative. So this would be, something a little bit less than negative pi over 2. So we should be getting our first loop. We should be getting our first loop within this region right here. Okay, well, let's see. Well, I guess if we started at 0 radians, we'd have a radius of 3. And as we go past pi over 2, a little bit past pi over 2, we're going to get we're going to be at the origin right here. So the radius is going to be getting bigger. Let's see, right at pi over 2, looks like right at pi over 2, it'll be at 1. So right at pi over 2, it'll be 1. This will kind of help guide us. So we're going to rotate. The radius is getting shorter. It's getting shorter. It's getting shorter. Just a little bit better. And then we're going to be back at 0 right here. And this is symmetric, so you could kind of think that we're going to have to do pretty much the same thing over here. Okay, beautiful. All right, well, now we have this little red loop, and that's going to be between, well, it'll kind of be this other region. It'll be between the number that's a little bit bigger than pi over 2, and it's going to go something a little bit less than 3 pi over 2. So that loop should kind of be contained somewhere in here. Okay, so if it's positive, if the radius was positive, the loop would be within here, but the radius here is negative, so as we rotate, actually the loop will pop out over here. So if we're exactly at pi, well, we have a radius of -1. Rotate pi, now we're at a radius of -1. Okay, and as we rotate from here to here, the radius is getting larger. So as we rotate, the radius should be getting larger. We should get this little loop that happens right here. And now once we're here, this would be the same region that we plotted right here. So what's really great, what's kind of cool here, is this blue hump at the top is giving us this big blue leaf, and then we're getting this kind of small little red leaf that's inside of this blue one. Pretty cool. Let's do one more. How about we shift it up just a little bit more? Just a little bit more. How about we do r cosine of theta? How about +2? +2. Go ahead and pause the video and give this one here a shot. Okay, let's do it. Okay, let's do it. Let's make our graphical t-table. Okay, let's see, we have cosine. Okay, the equilibrium's at 2. The amplitude's also 2. So I need to go up 2 units from equilibrium. So here we are at 4. Down 2 from equilibrium. Okay. Let's see, here's 2 pi. Here's pi. Here's pi over 2. Here's 3 pi over 2. Guess we could go backwards. Okay, so let's see. Cosine starts at the top of the amplitude. Okay, go ahead and bounce. So something like this. We could keep going if we wanted to. Okay. So what's going to be interesting about this is we're actually only going to get one leaf here. We have x-intercepts, or we'll be at the origin when we rotate pi radians or negative pi radians. So when we rotate pi radians, we should be back at the origin. Or if we rotate negative pi radians, we should be back at the origin. Okay, well, what's happening? Let's see. Well, maybe we'll start in the middle. So if we have 0 radians, we're at an amplitude, or we're at a radius of 4. So if we're at 0 radians, we're at an amplitude of 4. Or we're at a radius of 4. So we'll put this here. Okay. Now what's going to happen, I guess we could mark a few points here. When we're at pi over 2, we're at a radius of 2. So when we're at pi over 2, we're at a radius of 2. So the radius is going to start decreasing. The radius is going to start decreasing till we get to pi. Now when we're at pi, we're at 0. So what's going to happen is we're going to get bigger. The radius starts at 4, then the radius is going to get smaller, smaller, and as we rotate, we have to rotate all the way to pi, and we have to keep bringing our marker closer to the origin. So something like this. Okay, now that we're here, what's going to happen is now when we rotate, it looks like from pi to pi over 2, so from pi to pi over 2, my radius is still positive. So it's almost like we're going to bounce off. As we rotate, we need to make our radius bigger. And when we're at 3 pi over 2, we have to be at a radius of 2, and then when we're back at 2 pi, we are at a radius of 4 again. So we're going to be getting larger as we rotate. So for a whole half a rotation, we have to keep making our pencil go away from the origin, or our pen. So something like this. And here we have it. We kind of have this one leaf here, and it's got kind of like a little, I don't know, dimple in it. So we've actually seen this shape before. We saw this in the last video. This is a carnoid because, you know, it looks like a heart. This is a carnoid. And it's interesting because, you know, if this was just shifted down ever so slightly, we're getting this dimple right here because we're just bouncing off the x-axis. We're bouncing. The radius goes to 0, but then just comes right back out. If it was shifted down a little bit as we rotated, the radius would be negative, and it would have came in and give us a little mini loop in here. But when it just touches the graph, we'll just get a carnoid. Pretty cool. Let's actually go to Desmos and let's see how we can look at some cool animations of polar equations. We'll see you there. Hello everyone. Let's go ahead and take a look at some of those polar graphs in Desmos. So what we're going to do is if we want to plot something in polar coordinates in Desmos, we'll just use r and theta rather than x and y. So if we just type in, let's say if we type in r equals, let's do 2 sine of theta, something we graphed, so we got this circle. Okay, if we wanted to actually have this plotted in rectangular coordinates, you just use x and y, so you'd say y equals 2 sine of x, and then it'll plot it in rectangular coordinates. Here we're plotting in polar coordinates. Okay, and we can kind of maybe look at these side by side to see why we got this graph. In this blue, this is our graphical t-table. Well, when we're rotating and when we're going between 0 and pi, let's actually make some markers. Let's let x equal 0 and let's let x equal 2 pi. 2 pi. Okay, let's change the color of these. I don't know, we make these black. So I'm just looking at the graph, just one period of the graph. So what was going on between 0 and 2 pi is here we should get a loop or a leaf, and here we should get another leaf. Well, between 0 and pi, the radius is getting bigger. So as we rotate, the radius is getting bigger. Okay, and then when we were at pi, we were back to a radius of 0. And if we rotate a little bit more, so past pi, so we're rotating, from pi to maybe 3 pi over 2, from pi to 3 pi over 2, well, the radius is negative. The radius is negative, and so we're just going to be repeating over this loop when we're in this kind of bottom hump right here. Now, what's actually pretty cool is what I can do in Desmos is I can actually kind of animate how this is being drawn. So right now it's saying that r is equal to 2 sine of theta for theta between 0 and pi. Well, I could go from 0 to a variable. How about we call it m? Now, typically, Desmos, if you just type in a letter, it'll ask you if you want it to be a slider or not. Like, for example, if I click on the equation right at theta, and let's say I want to have a slider that changes the period. Let's say I just put an n here. Well, now it's asking me if I want n to be a slider, and yeah, I want n to be a slider. If I click on it, I can change the specifications on n. So, I don't know, let's have n go between 0 and, I don't know, we could do like 10, and let's do steps of 1. Okay. And that'll just change the period of this graph up here. Why is it not? Oh, because m. So let's change that back to pi. So now it'll plot. Well, let's put the n here. So now it'll plot this graph here for different periods, which is pretty cool. Okay. But if I want this to be a slider, like I want to put an m there, it's not allowing me to do that. I don't know why. I can just open up a new tab. I just hit enter. Let's just say y equals mx. Sometimes it likes, I don't know, it likes it when you define your sliders when it's within an equation rather than in a bound. So yeah, let's make m a slider, and then I'll just delete this piece. Okay, so let's have this go from 0 to 2 pi. So I want to graph theta from 0 to 2 pi. Let's click out of there. So if I open this up now and I hit play, notice here that it's graphing from 0 to m, or 0 to whatever number here I specify in this slider. So here it's kind of drawing the graph. So when we go from 0 all the way to pi, so pi would be what? That's roughly 3.14. And then when I go from 3.14, this is where we are. The radius is 0. The radius is 0. If we back up, here the radius is non-zero. It's non-zero. Okay, but now you can't really see it, but the graph is just starting to repeat itself when I go from pi to 2 pi. So that's pretty cool. Okay, but what's going to be more fun is, what happens if I let n be something different? So I don't know, how about we let n be 2? So now I see these between 0 and pi, I see these kind of 4 sections right here. So we could get 4 loops, and let's see. So as we rotate, this looks like between 0 and, well, what's this point right here? If I click on it, well, it's pi over 2. Between 0 and pi over 2, 0 and pi over 2, we're getting this first loop. We're getting this first loop here. Sweet. Okay, then what's happening? Well, between pi over 2 and pi, between pi over 2 and pi, well, notice the radius is negative, so the graph should make a loop over here. And let's see that. Sweet. Okay, so now we're at what? Roughly pi. So we're here, pi. Now from pi to 3 pi over 2, from pi to 3 pi over 2, well, the radius is positive here and it's getting bigger. So between pi and 3 pi over 2, we should get another loop right here. If we increase, we should get this another loop. And then we'll get our last loop here between 3 pi over 2 and 2 pi. And there we have it. So we can kind of go backwards and we just hit play, and we can watch how this would be drawn out. Pretty cool. Okay, well, what if we change the period? We thought n equals 3. So we could possibly have 1, 2, 3, 4, 5, 6. We could possibly get 6 loops. Okay, if we hit play. So our first loop is going to happen between what? 0 and pi over 3. So this looks like roughly an angle of pi over 3. So I'm guessing pi over 3 is roughly 1.06. So I'm getting our first loop right here between pi over 3 and now 2 pi over 3. 2 pi over 3 is this angle. Well, we should get another loop between here and here, except it's negative, so the loop will happen right here. So let's see. Sweet. Okay. So this is that second loop. Okay, this loop right here between 2 pi over 3 and pi, between 2 pi over 3 and pi. Okay, we should get another loop within here. And since it's positive, it'll kind of follow the angle. There we go. Okay, so now once we get here between, it looks like pi and 4 pi over 3 pi, and this is roughly 4 pi over 3, we should be getting another loop. But in this case here, the radius is negative, so we won't get a loop right here. We're going to get a loop behind. So it's actually going to start repeating itself. It's going to start repeating itself. So if I just hit play, there we get it. Pretty cool. And again, we could do more. You know, like, I don't know, we could let n be 4. We could let n be 4. Let's see what happens here. So here, this would be our first loop, second loop. So we could possibly get 1, 2, 3, 4, 5, 6, 7. We could possibly get 8 loops here. Let's see. In this case, we do all get all 8 loops. 1, 2, 3, 4, 5, 6, 7, 8. We got all 8 loops here. Now if I go to 5, well, we could get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 loops, but 5 of the loops are repeating over themselves here. So here we get this cool, I don't know, it looks like a sand dollar. And so I don't know if we want to just kind of, let's get rid of this and just see the kind of different shapes we could get for different periods. Just kind of hit play, just see what happens. Pretty cool. All these different cool shapes that we can get. Of course, we could go out much higher. Maybe this will just be fun to watch. Whoa! Pretty cool. And if I don't know if we zoom in. Oh, let's zoom in. See all these different loops that are happening. Pretty cool. Okay. Well, what happens if we shift the graph? So I think we saw what, 2. Let's do 2 cosine. Let's do 2 cosine, and let's do plus c. So c will be a slider. That's how I'm going to shift the graph up and down. Let's hide this for right now. So let's have this graph 2 cosine of nx plus c. So this will be our graphical t-table, and I can use the c slider to shift this up and down to see how it affects the graph. So let's have c, just have, sure, we'll have c go between, what did it have it set at? Negative 10, 10, that's fine. Okay, so let's see, let's go back. And let's let n go back to 1 for now. Okay, so if we, let's go ahead and plot this. So going from 0 to 2 pi, it looks like we could possibly get 2 loops. This would be this piece here, and this piece here would complete 1 loop. This would be the other one, but I think these are going to loop over one another. So we should just get a circle. Okay, well now what happens as we shift? Let's move this up a little bit. Ooh, let's go out, let's go back, let's go all the way out to 2 pi. It's repeating itself. There we go. So we should have gone, for this one, we should have gone around the circle twice. This would be looping around halfway, and then all the way around. This should be give us, I guess if we went from here, this would be going around the circle from here 1 time, and then this would be the second time. But if I let c get a little bit bigger, that second loop going around is getting a little bit smaller. Notice that the amplitude of that loop, I'm kind of using that word loosely, the amplitude of that loop on the inner part is decreasing. If I let c be a little bit bigger, that inner loop is getting smaller. The inner loop is getting smaller. And look at this larger loop is getting bigger because the radius up here can be larger. So if we move this, we can see all these different graphs that we can get here. And right when it touches the graph, that's when we get that carnoid. That's when we get the carnoid. If we let it go a little bit bigger, notice we'll actually never be at the origin because the radius will never be 0. So we could kind of move this further out, and we can see all these different kind of, this would be like a family of graphs. Pretty cool. Well, let's take this one and, I don't know, let's change the period. I don't know. Let's do something like this. Okay, so this was that cool 4-leaf clover. I think we saw it with sine, but I look like we're doing it with cosine. Okay, so we get this cool 4-leaf clover. Well, let's see what's happening. Well, this, if we go from, is this what this is? negative pi over 4 to pi over 4, negative pi over 4 to pi over 4. This will be that first loop right here. And this second loop right here is this piece right here. So if I shift the graph up, this leaf right here should be getting bigger, while this one here should be getting shorter. So let's see that. Notice that's exactly what's happening. This loop right here, this piece here is controlling this loop right here. So if we make it bigger, we get these kind of really cool shapes. If we let it go up a little bit higher, almost get kind of like an infinity sign. And then I don't know, this is like this reminds me of what of that guy on the peanut jar, Mr. Peanut guy. Look, we graphed a peanut. Here's the equation of a peanut. How fun. Okay, cool. Let's go back down. That's pretty cool. Look at all these cool shapes we can get. Pretty fun. All right, let's change the period even more. Okay, what if we let, I don't know, 3. Wow, we're getting, looks like there's this loop right here. Remember for this one, when we had n equals 3, these loops were like, we could have had a total of 6 loops. But half of them were repeating over themselves. So here's one loop and here's another one. But those inner loops are now shrinking. Look how cool that is. Look at this cool shape. And go out a little bit further. How fun. How fun is this? Whoa, cool. I don't know. Why don't we go to n equals 6? What will this look like? Let's shift this up and down. Pretty cool. Look at all these fun, cool shapes that we could get. And doing stuff like this would be really hard if we were just using, rectangular coordinates. It's a fun exercise. Try to convert these polar coordinates into rectangular coordinates and see how ugly they look. Well, it's because these shapes aren't well described using rectangular coordinates. They're much easier to talk about using polar coordinates. We can get all these super cool shapes. So make sure, come to Desmos. Check out these animations. Look at this cool stuff we can do. What if we change this to sine? Now it's just kind of slanted differently. Pretty cool. Well, I hope you're enjoying this as much as I am. Okay, make sure, Desmos is beautiful. I wish I had Desmos when I was in grad school. I didn't discover Desmos until I started teaching, but man, Desmos is so much fun, so easy to build these really cool different animations. So, have fun. Okay, that's all I have to do talking about polar coordinates or graphing polar equations. In the next video, we're going to start talking about graphing what are called parametric equations. We'll see you there. Take care.